And
Okay,
so,
cool.
so as you can see, everything, everything is named except for Ligure.
Mm-hmm.
And all right, so I'm just going to keep going, and hopefully the rest of the people will catch up and figure out that it was an accident that I was cut off in mid-sentence rather than. And I don't know how much of this everybody heard. I think I was on this slide, and I had gone through a couple of other names that had been thrown out for what people thought was zircon until it got to the bottom one in the 1780s, where Abraham Werner finally used the word zircon. There's Don, and a few other people hopefully have rejoined as well. And so I'm just, yeah, there's Ron as well. So I'm just going to keep going. And so I've gone through all of these names, and the real question is, besides the fact that it sort of piqued my curiosity, why did I do it? And here's the reason. Zircon has been traded as a gem for well over 500 years. It was pretty much not a gem of any interest in the West, but in the rest of the world, it was very important. And it was traded under all of these historic names to describe the various colors and kinds of zircon gems that were in that trade. And so you've got jargon, you've got jargoon, you've got melochrysos, and you have either hyacinth or jacinth for all of these different colors and kinds of gems. And most of them in the rest of the world are still in use. And so you will run across them all of the time. And unless you know what they stand for, you have no idea what a dealer in some place other than Europe is talking about. And on top of that, there have been more unofficial trade names added within the last 100 years approximately. And I've listed a whole number of them. And some of them are used very often, like beckerite and sealand and ceridolite and starlight in particular. Those are used even in the West. And so you have to have some idea of what all of these names are about in order to sort of keep up with what gems are and where they come from, because modern descriptions aren't always used. People fall back on these historic names, except, as I said, in particular in the US and for the most part in Europe. So let's go back to the gem part of zircon. These are natural zircon crystals, and they're ugly as all get out. Almost all of the crystals that you find are these opaque colors from gray to black. And most of the really dark colors are caused by the fact that when zircon crystallizes, it traps iron oxide. The important part of these crystals are the ones at the far right, those pebbly looking things. And those are water-worn crystals because most zircon is found in alluvial gravels, rocks washed down rivers. Another interesting thing, since I talked about it in the case of beryl, is that the largest zircon crystal is about 7 kilograms, even though it's not very large. And the reason for that is that zircon is really, really dense compared to most other minerals. And so a little bit of zircon goes a long way as far as carat weight is concerned. And that's another thing to be aware of when you're talking about how big is a gem. Because when we were talking about beryl, we talked about the fact that there isn't a one-to-one correspondence between size of a gem and carat weight, except in diamond, and beryl is a little bit off, but zircon is a lot off. And so just because you know the size of the stone, you don't have a clue by using diamond as an analogous substance. In any event, that stuff wasn't used for making gems. It couldn't be because it's not transparent or translucent. So this is what gem quality crystals look like, and it's called gemstone rough. What the faceter, the master cutter, uses to form a gem that'll go into a ring or some other piece of jewelry. And the interesting thing is, as I said, zircon is extremely rare. And so quality crystals of any color at all are very unusual and hard to find. The other thing about zircon is that it should be colorless. It's allochromatic. There's nothing in the formula that should absorb light in the visible. On the other hand, it looks like that top row. If you can find a crystal, it's almost always in that yellowish to dark brown range. And very seldom do you find an orange or a red crystal like the two on the bottom left. Even rarer, you can find green crystals, and colorless crystals are very, very, very rare. And blue crystals you almost never find, especially these days. Now that's very weird, as you will see, compared to the gems that end up on the market. And so there again is the schizophrenic personality of zircon. Certain colors are important, especially in the US and also to a lesser extent in Europe. There are really browns and all of these other colors are perfectly fine for the majority of the rest of the world, but the crystal colors that people are interested in this country are almost never found. So the next thing is that there are at least 4,500 different locations where gem quality crystals can be found. Most of the world's supply, however, comes from these alluvial gravels, stuff washed down rivers, primarily in Cambodia, Sri Lanka, and Thailand. And the Sri Lanka gravels have been mined for over 2,000 years and were the major source for most of the stones that were eventually traded around Asia. On the other hand, as I said, zircon can be found all over the world. So when you start talking about Egypt, there are places where the Egyptians traded that have zircon. And so they didn't have to go to Cambodia or Sri Lanka to get their crystals. In any event, Sri Lanka still produces the greatest variety of colors and most of the truly large crystals in the world. And that was especially true in the old days. Cambodia and Burma and Thailand are also fairly important sources. And each of them has supplies of different colors. And now minor areas like Tanzania and Madagascar are becoming important as sources of reddish gems. But the important thing is, because of the rarity of any good crystals of zircon, material from anywhere, even tiny deposits, are often used in the gem trade. And so you can see that you have places like Madagascar, as I said, but also Brazil and Pakistan. And there are even crystals in Oklahoma. So all over the world. And you never can tell for sure where a crystal came from that was turned into a gemstone. Now, when I talk about mining, this is what mining of zircon looks like. And it hasn't really changed in the last 2,000 years. As I said, zircon has been mined in Sri Lanka since about 500 BC, when the Indians conquered the island. And you can see essentially how zircon crystals are found. Somebody picks up a pan full of gravel and then sorts through it by hand. And the only thing that's different since the earliest days of mining is the fact that you're now starting, especially in a place like Sri Lanka, but also in Thailand, to get large-scale gravel mining, basically getting as much gravel as possible to sort. And so you have what are called the lama mining pits in Sri Lanka these days. They're usually less than 20 feet deep, but they can be, and they're lined with timbers to keep them from collapsing. And they can be as much as maybe 30 or 40 feet by 30 or 40 feet. And you have a guy down in there pulling up gravel in buckets and giving it to a guy with a big pan to sort by hand. So that part of it hasn't changed in thousands of years. And in Thailand, it was a little different, because before 1400, it was a sapphire mining byproduct, because sapphire is mined the same way. And it's also mined, lots of gems are mined this way in places like Brazil. Large scale, somebody takes a water hose and washes the gravels to get rid of all the dirt. And then somebody scoops up the rocks and sorts through them looking for crystals. And the same thing is true in Cambodia. So this has been going on for thousands of years. And it's only recently, probably in the last less than 50 years, that even though Cambodia is an important source of zircon, that they've started to dig shafts, and they dig little ones. And basically the way they look for all of this stuff is they take a long metal rod and they stick it in the ground until they hit a rock. And they say, aha, gravel is down there somewhere. This is an old riverbed. And then they start looking through the gravel. They take the top layer off, like they're doing in that lower left picture, and they start sorting the gravel. And so this is because zircon crystals are so rare and the market for good zircon is so small, this kind of mining is not just necessary, but it's adequate to feed the gem market for zircon. All right, so now zircon gem varieties, just like I talked about beryl varieties. In spite of all of those strange names that were used for all the different colors, in the West, varieties of zircon are now officially, as opposed to all those unofficial names, designated just by color. So it's red zircon or yellow zircon or brown zircon or colorless zircon. And the problem with that is multiple fold. First of all, if you look under other gem colors, there are all of these subtle distinctions that can significantly affect the value of a gemstone. And so you can have yellow and yellowish green and blue-green and greenish blue, and each of those is a different color. So when I'm saying color, it's not just a primary color, it's one of these very subtly different colors. The other thing are several other things, but most importantly, even though I said that blue crystals are almost never found, blue is the most popular color in the West. It became fashionable in the late Victorian era, the late 1880s, and it has over 80% of the gem market for zircon in the United States. Now, in the old days, there were large crystals of blue, and they ended up in estate jewelry in English nobility. And so when you start talking about large blue gems, basically that estate jewelry is taken apart and turned into some other kind of jewelry, because there just aren't any large blue crystals being found anymore, natural ones. The other thing is that colorless, as I said, is exceedingly rare, but we figured out how to make colorless zircon. And so it's been used as a diamond substitute since the early 1900s, but now it's synthesized, so we don't have to find natural colorless. And then finally, the weird thing is that outside of the United States, brown zircon is extremely popular. It's one of the major gems in the gem trade outside of the US. Now, inside the US, brown gems are considered disgusting, very undesirable. Any other kind of gem that's brown would never be used in jewelry. But the rest of the world thinks brown is beautiful, especially in a zircon. And so you have all of these different, again, color distinctions that are not just brown. You get yellow brown or honey, which is very popular. You get reddish brown. You get the color of tobacco. And then the one that I really have never found a picture of is black tea. I have no idea what that color looks like, but it doesn't sound like a gem I would use for anything. And so, just as a general rule, most zircon gemstones, crystals, and then the gems produced from them are small. So any zircon over 3 carats, which is really tiny, is considered large. Now the blues and the greens can be found up to about 10 carats, and in some unusual circumstances, you still find ones up to about 20 carats, but most of the really large gems are recycled, again, from Victorian jewelry or from jewelry in some other part of the world. Now, yellows and oranges are common up to about 5 carats, but really not often that big, and you almost never see anything over 5 carats except in a museum or some private collection somewhere. And then finally, the reds and the purples are really tiny, much less than 3 carats in general. And so if you can get a good 1 carat red zircon, that's considered a very valuable gem. So a very, very different kind of market for gem zircon than for almost every other kind of stone. Now, GIA, Gemological Institute of America, this is their collection of natural zircon colors. And you can look through it and see the different cuts and the slight variations in size, but nothing outstandingly large, or too small. But the most important thing to notice is they don't have any colorless or blue gems in their collection of natural zircon colors. As I said, natural blues and colorless are extremely rare. And then if we look at the Smithsonian collection, the important ones are in the center. And those are museum quality, as I said, and they're large. I mean, the colorless one is only just under 50 carats, but the others are about 100 carats. And then for completeness, there's the small gem called golden color on the left, and it's included in the Smithsonian collection because it's a large gem from Madagascar. So Madagascar is a new source of zircon gem quality crystals, but they're all fairly small, although that's almost 7.5 carats, which is a pretty good sized stone. And on the far right is a stone from Tanzania. And it looks red to most people, but it's actually called orangish brown as its official color designation. And again, Tanzania is a source of most reddish gems these days, and that's a very large gem at 30 carats. And then there's a red brown and a couple of very large browns from Sri Lanka in the collection, and also one pure green. The greenish one that's up there on the top is actually considered off green. See if I can remember. There it is. It's called yellowish green. And you can see that it has an undertone of a yellow associated with it. And so even rarer is a true green. And the biggest one in the Smithsonian collection is under 25 carats. But those are all really unusual stones. Now, where do all the blues and colorless stones come from? And the answer is zircon, especially since the 1920s, has almost all been heat treated. Now, heat treatment's an accepted practice for a lot of different kinds of gems, like for sapphires, for example. And basically, when you heat a sapphire, what you're doing is you're distributing the impurities in that sapphire that cause the color. And by distributing them, the color of the gem becomes more even. Now, that's not why zircons are heated at all. So the first thing you got to know about zircons is that crystals are classified as high, medium, and low. And high crystals are clear and defect-free, and they're very, very rare, and they're used to produce nearly all high-quality gem varieties. So again, you've got zircon crystals, but even that pot is smaller because you only have these what are called high crystals. Now, the medium and low crystals appear cloudy. No matter what you do, they look cloudy, and they're called metamixed. And metamixtion is caused by damage to the crystal structure from those uranium and thorium impurities and the radiation they produce. So that radiation hits the crystal structure and starts destroying it. And low crystals, and for whatever reason, they're usually green, low crystals can be so destroyed that there is no crystal structure. They become amorphous, they're glass-like. And medium crystals are generally saved in the gem trade. There's a low temperature, 900 degrees centigrade, heat treatment that can be used sometimes to improve the clarity of those crystals so that when they're very small, they can pass as decent gems. and be used in the gem trade and in jewelry. Now, low temperature heat treatment is also used to change the color of a zircon crystal. And so if you start with brown, which is what most of those natural crystals were, some will turn colorless or yellow when heated in the presence of air.
Oxygen or air?
Excuse me? David, did I hear you make a comment?
Oh, can you hear me?
Yes.
Oh, I thought I was muted. I'm sorry. I was thinking that I was thinking oxygen. You said air, but oxygen is without nitrogen.
Yeah, well, the
Is it
oxygen in the air, the oxidizing process is what helps change the color. And I'm
Okay.
not going to go into, I'll mention it now that you've brought it up. I'll mention why that is when I get a little later in the talk.
Yeah.
But the important thing is that that process, turning brown crystals colorless, was the source of all colorless zircons before synthetics, because otherwise zircons are too rare. There would never be enough of them to use as diamond substitutes. The other thing is that orange brown or reddish brown stones can turn yellow or even red, and you never know what's going to happen when you start with one of those ugly colored crystals and you heat it. And the problem with those reddish or yellow ones is the colors can fade in sunlight. And so you don't know if that's going to happen, but the effects can be reversed sometimes if you treat them a second time. But if you keep heating them, the material, the crystals actually become fragile and they start chipping and they get really hard to cut and they won't take a polish. So there are limits to all of these kinds of heat treatments. Now, this all sounds pretty sophisticated, but this is the kind of heat treatment oven that's used. And this one happens to be in Cambodia. And so you've got all of these refractory bricks, and the heating is often done directly at the site where the crystals are found, because the miner wants to get the maximum price for those crystals when he sells them to a dealer in rough, the middleman who's going to pass them on to a cutter of some sort. And so they maximize a brown crystal by heating it themselves and trying to, pass on the best quality gem they can. Now, blue zircon is different again. Natural gem blue crystals, as I said, are very, very rare, and these days almost never found, although small quantities are found in Cambodia and even smaller amounts in Burma. So where does it all come from? For example, starting in the 1920s, because of the demand of the US market, just like aquamarines are treated to get rid of the greenish color and make them as blue as possible, blue zircons started to show up, were marketed under that starlight that I was talking about as one of the trade names, recent trade names, under starlight blue. So that's produced by heating reddish brown or some brown at what's called high heat, about 1,000 degrees centigrade. And that's done for several hours in a reducing atmosphere with no oxygen present. And the more reducing the atmosphere, if you're lucky, the darker the blue you get. Now, the problem is that only some material, brown material, turns blue. And most of it's from specific deposits in Sri Lanka, and a little bit of it's from Thailand. And so again, this is a crapshoot. You've seen those poor people standing there with these big, in the water with these big pans looking through tons and tons of gravel to find a crystal, and then somebody sticks it in an oven and it gets ruined. It turns some weird color, or it cracks or something like that. And this again is a very, very sophisticated process. And you can see the oven that's used over on the left. And because this is much more complex, you got to control the heat and you got to keep the furnace sealed so that there's no air, and you want it to be a reducing environment. So it's actually done in the presence of charcoal. Most of the rough in this case, wherever it's found, like Sri Lanka or Burma, is shipped to Thailand, where they have expert cookers, the people who know how to man these ovens and get the color just right. Because if you heat for too long, the color is ruined. If you don't heat for long enough, you don't get enough color. And once you open this, you can't reheat it. And so again, you got to really have a knowledge of the art. Now let's talk about some more weird properties of zircon. If you don't facet a zircon properly, even a clear gem will appear blurry. Regardless of that, basically what you have to do is line up the crystal, if you can figure out the direction of it, so that you're looking down the C-axis when you're looking at the top of the crystal. And if you do that, you can get away with a diamond round brilliant cut, where you have 56 facets on the bottom of the stone. But for really high quality gems, especially large ones, the faceter will use what's called a zircon cut, and he'll put 8 extra facets on the base of the stone, the bottom, the pavilion, the pointy part that's also called the culet. And if you look at the pattern of the pavilion here, you can see that it's that star shape as opposed to sort of an in multiple star in the center, as opposed to a radiating star that you see in the brilliant, especially in the colorless one. Now, this is not done for just any old zircon, because doing this kind of faceting requires additional skill and much, much more labor. And so it's only for the highest quality gems that you will see this kind of cut. So that's one unusual property. And so you can see that more and more of these unusual treatments and labor have to be expended in order to make a good zircon gem. Now, the next thing is, where did that blurry come from? And the answer is, it's because zircon has what is called double refraction. It has different refractive indices depending on what direction the light travels through the crystal. And you end up with exceedingly high double refraction in high undamaged crystals. And gemologists use what's called a refractometer to actually measure the difference in the directions of light going, or the speed of light going in those different directions through the crystal, and get a ratio that's called a refractive index. And at the end of the talk, I'll actually show you what a refractometer looks like, because I have a simple one in my little gemology lab. But that's a key step in identifying most gems. And even in my little instrument, I can measure the refractive index to 2 decimal places, where the second decimal place, the hundredths, is real. And there are tables of all of the different kinds of minerals that can be cut as gems. And so by measuring the refractive index and looking up the number you get in that table, you can identify about 95 to 99% of the gems you're ever likely to run across. I've had a couple, and even some of my gemologist friends have run into trouble identifying some of those C and D, the rarest of the rare minerals that are cut as gems, but most of the time, no problem. Now, the difference between the gem's highest and lowest refractive index, not the ratio, but the difference, is called birefringence. And zircon, for good crystals, has among the highest birefringence you will ever run across. At that 0.059, that doesn't sound like a big number, but it's a difference between two numbers that are approximately 1. And so that's a big number as far as birefringence is concerned. And for those very low or amorphous crystals, birefringence approaches 0. There is no difference in the speed of light going through the crystal in any direction. But what birefringence does is it produces a phenomenon called pleochroism. And if you look at the bottom, that's the same crystal. And it looks like it has different colors because you're looking at it from different angles. And that difference in color is called pleochroism, and it's caused by birefringence, which is caused by this difference in refractive indices in different directions through the crystal. Now, this is why all of that happens. And I don't expect you to be able to really get a good picture in your mind by looking at those diagrams or illustrations on the right side. I mean, I'm a crystallographer, among other things, and so I can look at that and I can understand exactly what I'm looking at, but I don't expect that you will. In any event, zircon is tetragonal, and so the A and the B directions in what's called the unit cell are the same number. But in the C direction, it's a slightly smaller number. And so what you end up with is crystals that look like those idealized shapes on the upper left. And you can see that you can actually find dipyramidal or prisms with a pyramidal top in nature. They're rare, but you can find them. But the important thing is that if you understand the pictures of the crystal structure, especially the one with the blue and the green dots in it, basically what you're doing is you're looking down the crystal from the top. And if you know how to interpret that picture, what you see is that you basically have sheets of all of the heavy elements, the zircon in particular, in one direction in that sheet. And so you've got sheets stacked on top of each other. And all of a sudden you can understand you've got all of these heavy atoms which are slowing the light down as it goes perpendicular to the C-axis and go much faster when they go down the C-axis. And so that's the difference in the refractive indices in those two directions. And that difference causes the birefringence, which causes the pleochroism. Now, in zircon crystals or gems, it's really not that important. But in other gems like tanzanite, tanzanite has even lower symmetry. And so it has 3 refractive indices, depending on which direction the light goes through the crystals. And in that case, you can get dramatic changes in color. You would like a blue, but in certain angles, what you see is purple. And in other angles, what you see is red. And in extreme angles, you can see flashes of green, all in the same stone by looking at it from different directions.
Beautiful.
And so that one has pleochroism in 3 directions, not just in 2. And so zircon's a piker in that regard. And another property of zircon, which is interesting, is that it fluoresces strongly under UV light. And so even though in my screen, pictures of people are slightly overlapping the pictures on the upper right, you can see the same stone in visible light and then the same stone under UV light. And basically what looks like a black stone is fluorescing that yellow-green color. And so that's called the emission. And that emission can make a gem look yellowish or greenish or even orangish red under UV light. And where is that all coming from? And the answer is primarily from these 3 different situations. And you'll see what a color center is in zircon in a bit, but that's a color center that's produced by the internal radiation of the crystal. And that has a peak of emission, not absorption now, of emission in the yellow. And then if you have the lanthanide dysprosium in the crystal, you end up with peaks in the blue and yellow. And so together they produce a greenish color or a yellowish green color. And then finally, on the right, if you have europium and samarium in sufficient quantities, they produce peaks in the orange and the red. And so you get that orangish red mix depending on the amounts of those various lanthanides, rare earths in the various zircon crystals. And so, as I said, all zircons have rare earth elements in them, but they don't always have the same amount of all the lanthanide elements in them. And so again, that becomes a fingerprint for a particular gem as far as what's going on in the crystal. Now, finally, and this is usually the first thing I talk about when I'm talking about gems that are colored. In the case of zircon, what causes the color is a mystery still. It's an active area of research, but there is no definitive answer to what's going on. So, as I said, zircon should be allochromatic. It should be colorless because there's nothing in the formula that says it should absorb visible light. And as I showed for beryl, it's an allochromatic mineral, and its color is caused by different transition metal trace impurities. But that's absolutely not the case in zircon because nothing fits in zircon. Nothing has a high enough charge or is the right size, with the possible exception of niobium, which is the next door neighbor to zircon in the periodic table and is also a high field strength element and can have cations in the +4 oxidation state. And if that's the case, niobium will produce a red absorption color. However, niobium is a really unstable material, and it doesn't like the +4 oxidation state. And so it's usually either in the +3 or the +5, or sometimes in the +2 or the +6. But it's really hard to get niobium in the +4 oxidation state. And so that's pretty unlikely to be a source of color. Another possibility is the fact that uranal cation, uranium +4, also absorbs, but it's pretty bad at it. And it usually produces a very pale yellowish green. There's a special kind of glass that used to be made that incorporated uranium. And it was called uranium glass, but it had some other name that starts with a B that skips my mind. Vaseline glass is what it used to be called. And it's very pale. But the good thing about it is because of the uranium, again, you end up with defects in the structure of the glass. And so that Vaseline glass glows green under UV light like you wouldn't believe. But again, the unlikely coloring agent for zircon of any kind is uranal cation. The other mystery is that gems of what appear to be the same color from different places end up having different absorption spectra when you look closely. So you can take a red gem from Tanzania and a red gem from Madagascar, and if you look at, they both look red to the eye, but if you look at the details of the absorption spectra, they're entirely different. And so no one thing in zircon is always responsible for a particular color. And as a result of that, looking at a zircon and deciding that it's got X impurity or Y impurity is impossible. Now, two theories are proposed for the actual coloring agent in zircon gems. And they're both probably right. And they both might happen at the same time. And how can that be? So first of all, as I showed you in the previous slide, when rare earth elements are incorporated into zircon, they're incorporated in the +3 oxidation state. So they fit because they're high field strength elements and they have a high charge and they have about the same ionic radius, but they have the wrong charge compared to zircon itself. And so they act as positive holes in the crystal, right? So an electron from somewhere else, when it gets excited by light, wants to jump into that hole. And that absorption of energy causes the color. And so dysprosium +3 causes yellow color. Gadolinium causes green and erbium causes red. But all the other rare earth elements also cause some color in the visible spectrum. So again, depending on how much of each of those 14 lanthanides is absorbed by the zircon when it's precipitating out of that fluid in the pocket will determine something about how many of these positive color centers it has and how intense the color will be. And the answer is, as you can see from most of those crystals, the color is usually very, very intense. Now, the flip side of those positive holes in the crystal is absorption at F centers. And we saw those F centers, negative holes in the crystal, where there isn't anything at all, right? And basically what you have instead of an atom in the structure is an electron in the hole left by a missing atom of some sort. And in the case of zircon, those negative holes, those F centers, Fabry centers, are caused by the same internal radiation that's destroying the structure. Along the way, basically you get those negative holes. And so all of these different holes act as absorption centers for visible light and end up giving that very intense color that most zircons have. It's very seldom that you see a pale zircon. And the fact that you have these color centers also tells you why the various heating processes work to change the color of zircon. And the answer is, especially in the case of negative holes, heating and oxidizing can change and make those holes disappear. And so suddenly you started with a brown gem, you oxidize it, the holes go away, and suddenly you have a colorless gem. Or if you're lucky, you take a brown gem and again, you reduce it and you turn it into blue. And so this is why that heating process or those heating processes work. You're doing something to affect these positive and negative holes in the original crystal that are giving it color. And I think, yeah, that's the last slide. And so let me get rid of the slides by stopping sharing. And now what I want to do is get me in the center. I don't know exactly how to do that. But what I wanted to do was show you what the actual instruments are that I was talking about. Now, gemologists have really sophisticated versions of these tools in their laboratories, but I'm cheap, and so I have really simple ones because I'm not trying to be a licensed gemologist and do anything fancy or too fancy. But still, as I said, with my little simple tools, I can identify something close to 95 to 99% of all of the gems I run across, including those D ones. And so let me, Don, how do I get me to be the center of attention here? I don't know how to do that. I want me to be the center of attention, Don. Do you know how to do that?
I think you already are.
You are, Steve. All we do is we
Oh.
just touch on your image and you're now, we see you fully.
Okay, well, I don't see myself, which is why I was confused. In any event, I'm holding this up. Can anybody see that?
Lower it a bit. That's good.
All right, it's just a little tube and it has lenses at both sides. And those lenses are actually prisms. And this is called a dichroscope. And so basically what you do is you hold one end up to your eye and you put the gem that you're interested in front of the other end, and you look at a strong light. And that little instrument will tell you something about the refractive index of the gem you're looking at. In particular, it will tell you about the symmetry of that gem. There will be no dichroism difference in color in the two halves of the prism if you have a gem with cubic symmetry, and there are a lot of them, be like the zircon, the cubic zirconia, but there's lots of others besides that in diamond that in fact have cubic symmetry. And then you can actually estimate roughly whether you have a gem with a high refractive index or a low refractive index. And so that's a real quick and dirty test, and no moving parts. This thing cost about 50 bucks. It never wears out. It never dies unless you drop it or do something horrible like put your finger on the special lens. And I keep it in a special case, and then I stick it in a box like this. And that's a tool that I use all the time because of how simple it is to use. And now I'm going to show you my refractometer, which is another situation entirely. And it's in this really fancy case to protect it because it's got some delicate parts, but again, nothing moves. And so the first trick is to remember how to get it out of the box without killing it. And there it comes. Okay. And so it's got the box and it's padded in several different layers. And then on top of that, it's in this zippered case. And it's got a handle on it so you can actually carry it around. And I actually, when I'm interested in a particular gem, I will take this to, I used to, I don't do it anymore, but I actually used to take some of these instruments to a gem show. And I would actually test a gem in a lot of different ways before I would buy it if it was a rare gem. And you couldn't absolutely tell what that gem was just from the color. Or the best answer, of course, is you buy from a reputable dealer, but sometimes you're looking for something and you don't know anything about the dealer who's got one. And so now I'm going to, this is just a little box and it's got a lid and it's got a little viewing thing. Can everybody see what I'm doing?
Yeah.
All right. Basically, what you do is you take the gem you're in. Oh, God, I shouldn't be doing that. You take the gem you're interested in and you put it on a little window in the flat part of this thing with the flat part of the gem down. And then you close the lid and you push a button on the side and it's got a battery and that turns on a light. And so there is a moving part. You've got the lid and you've got the button to turn the light on and off, but that's it. And then you look through this lens and it's got a little gauge on it. And you actually look through that and there's a light source that you can use independently of the internal one in this model. And basically, you end up with a reading, as I said, to 2 decimal places of what the refractive index of that gem is. And then all you have to do is look up that number on a table. And 99% of the time, that will tell you which gem it is, because somebody has taken a $5,000 version of this and measured all of the known gems to produce that table. And so this is a pretty reliable technique and it almost never fails. I know of one instance, I bought a gem from a gemologist friend of mine, whom you know, Mary. I bought one from John.
Yes.
And it was a very rare gem because he's a dealer in gems and a very reputable one. And I've known him for probably 20 plus years by now. And I bought a lot of rare gems from him.
What's John's last name, Steve?
Rhodes, R-H-O-D-E-S. ADS, I think. And
D&J Rare Gems.
yeah, and he is a master faceter. He's won all sorts of awards. And whenever I've wanted a really good gem to pass on to one of my kids for a piece of jewelry on a special occasion, I've always had John cut one for me because of the quality of the work that he produces. But in any event, I bought a gem from him, and somehow it didn't look right when I measured it on the refractometer. I was getting a reading that was a little bit off. And so that gem ended up going to a gemologist friend who's a consulting gemologist in Princeton. And she does this for a living. She figures out what gem is what for really high priced clients. And she has a gemology laboratory that probably cost, at least $25,000 and probably closer to $50,000 with all of the instruments that she has, top of the line of everything, compared to my probably $500 or less investment in all of the instruments that I have in my little laboratory. And that includes fancy microscopes, polarizing scopes, all kinds of things. In any event, she looked at the gem and she decided I was right and John was wrong. And it turned out to be an even rarer gem than John thought it was, which was the good news after all of that. But this was a little tiny gem that was about 30 points, right? So 30 hundredths of a carat. This is a little tiny gem. And all of these measurements that John made and I made and she made were done on this little tiny gem to figure out what it was. And that's basically the typical nature of the gem trade. Now, I talked a lot about zircon as a gem. And as I said, it's schizophrenic. It's formed in two different ways. It's rare to begin with. And then most of it is spread throughout the world in little tiny crystals that are useless as gems. And so that small supply ends up being an even smaller supply of crystals that are formed in those pegmatite pockets. On top of that, most of those are contaminated, and so they're useless. And then you end up with little pieces that are washed down in streams from the original pegmatite somewhere up in the mountains. And they were washed down from those mountains, some of which are no longer there. They existed so long ago that they've worn down to almost nothing, and they look like little hills. And so you can't look for the mother lode like you would for gold up in the mountains in the Rockies or something like that. So you find them in these little pebbles in these stream beds, some of which are active. And there are lots of gems that are found that way, like garnets. And one of these days I'll talk about garnets, because garnets are another one of these gems. Garnet is a gemstone, and then garnet is also a group of minerals. And garnet as a gemstone is not one mineral. There are at least a half a dozen identifiable minerals, all of which have the same structure and are used as garnets in jewelry. And they're all different colors. And so you can find garnets not just in the traditional red, but you can find greens and yellows. And there are even colorless garnets, which is probably one of the rarest kinds of all. In any event, when you really get into a lot of gems, I started with beryl because it's probably the simplest to understand as far as what the mineral is and what the structure of that mineral is and what the impurities are that cause all of the different colors in the different gem varieties of beryl that are used, like aquamarine and emerald and so forth. Zircon, as you can see, is a totally different story, and it's not the most complicated of the bunch. Anyhow, I'm done. Questions?
Thanks, Steve.
Thank you. So how many minerals are on Earth?
Officially, there's
Anybody?
almost 5,000.
Right. We had a speaker at the Linus Pauling lecture series that said it was like 4,600 or something.
Yeah, it's
And
40,
how many are? And it said that on Mars and maybe another, maybe Venus, that they only had about 600 of minerals, and most of the ones that why Earth has so many is because of biology. Is that how you understand it? Life.
Yeah, that's a
Would you
part
say
of
it that
that's a
way?
part of the story, but there's also oxygen. And oxygen has played a
Oh,
huge role in changing one kind of mineral into another. And so you have metamorphosis in the earth as well, from internal heat, fairly high temperatures near the surface of the bottom of the crust or in volcanic vents. And that actually, like in the case of garnet, most garnet should be mafic. It should come out and stay right at the very top, but it melts. And so it ends up coming out of the ground as garnet, and then gradually it turns into other things. And those kinds of processes only happen in a planet that has high core temperature and molten core and volcanism. And there is a certain amount of volcanism on Mars, but not very much. Certainly not anything close to what there is on the Earth. And it doesn't seem like there's true volcanism on Venus either. And so that to me is one of the reasons that there are many fewer minerals. I talked a little bit about that in terms of the minerals that you find in meteorites or basically in asteroids that are, disintegrated old planets. And I talked a little bit about that. And then I've also talked about the fact that the minerals on the moon look like the minerals on Earth, because once upon a time, the moon was part of Earth, at least according to almost all of the theories that are out there. And there's lots of reasons to think that that's true. And so it depends on where you go in the solar system as far as how many minerals they're going to find and what kind there are.
So in Oregon with its volcanism and in the Sierras like Yosemite where there were big granite deposit that then gets exposed, would you find these zircons there?
You'll find those little tiny ones, essentially all volcanic felsic rocks like granite and rhyolite have zircon in them. And I'll talk about how important that is scientifically in part 2, because zircon has so many scientific applications that it's hard to imagine.
Huh.
I mean,
Mary, did you have a question, Mary?
Yeah, I did. With pegmatites, they seem to be a source for a lot of gem material. Besides zircon, beryl, and tourmalines, what else can you find in pegmatites?
That's a very good question.
I mean, off the top of my head, if I remember correctly, you can find things like chrysoberyl and fluorite and probably a half a dozen other common gem minerals in pegmatites. So the flip side is it's unusual not to find a gem mineral in a pegmatite. That's much more common. I mean, and we're talking about like the 20 common gems.
Mhm.
When you get past that, all bets are off. But probably 80, I would guess 80% of all of the minerals that produce transparent crystals and are cut as gems can be found in pegmatites.
Mhm.
I mean, sometimes those pegmatites don't look like pegmatites anymore. Like if you go to New Jersey, there's a huge quarry that's basically weathered pegmatite, and it's got hundreds and hundreds of different kinds of rare minerals in it. It's Franklin is, if I remember correctly, is the name of the quarry. And that Franklin mine produced the first specimens of I don't know how many minerals. And that's because it basically was one giant pegmatite pocket,
Mhm.
you know, because there really hasn't been a whole lot of volcanic activity in New Jersey lately. And so it's really, really old. And
I
so
know that there are places in Maine where you can go and do gem hunting in their pegmatites there, but I think it's mostly tourmaline that they find there, schorl and some things like that.
right. In the barrel talk, I actually showed a picture, an old time picture from the 20s of a mine in a giant pegmatite cavity. That's a tourmaline mine, and
Mhm.
it's been going since the late 1890s, and it's still active, and they're still finding tourmaline in it.
Mhm.
And it's big enough for somebody to stand in it, but that's a little one compared to some of the pegmatite pockets that are used for mining.
Mhm.
Thanks very much, Steve. I've got to take off. Really appreciate your doing this. Take care.
All right,
Yes.
and I presume people really want me to do a part 2
Yes,
and talk
Yeah.
about all of the scientific applications of zircon.
Definitely. Yeah.
We've got a book for next week, don't we? Is that how you wanted to do that?
Did I say that?
Maybe you said you were gonna do another one in between or something.
No,
I
I sort of remember, must have been must have been really late at night, and I must have been dreaming or something. You know, I was very tired, but I will do that because I basically have all of the slides I need in order to do that kind of a talk. It's going to be pretty technical, and I am going to talk about petrology, where rocks come from, and how zircon can tell the history of those rocks.
Hmm.
I'm going to talk about how zircon is used as a clock in everything from archaeology to a half a dozen other sciences And I'm going to talk about a number of other things. I might even throw some creationist arguments in for good measure.
Great.
So I didn't actually prepare an outline for part 2, but those are the kinds of subjects I'm going to talk about. Does that seem reasonable?
Mhm.
Okay, well, at that, I think I'm going to be the one to leave first because I'm sure it's past my bedtime. Take
Thanks
care,
again,
everybody.
Steve.
Thanks for joining.
Thanks for,
Yeah.
thanks, Steve.